Okay, I think we can start section 4.4, which is on the fundamental theorem of calculus. So sounds important, and it actually is. This is something we're going to use over and over again. This is supremely useful, and the basic idea of it is this. If you remember from 4.1, right, which is on your previous test, we were talked about these indefinite integrals. We also call those antiderivatives, right? Antiderivatives, same thing as indefinite integrals, right? And, these are just some other functions which we call capital F of x, but you can also add any arbitrary constant to those, right? So indefinite integrals are functions, right? But they're functions plus any arbitrary constant, right? So that's the idea of a definite integral. And in the last couple sections, we talked about definite integrals, which are just numbers, right? So these are just numbers, and in fact, they represent the area, right, under the graph, under the graph of the function, right, between a and b. And of course, the area will just be a number, right? Could be 0, could be 108. It could even be negative, in which case we have to worry about, that it's not going to be the area. So we're assuming that f of x is positive here, or non-negative at least. But if f of x is negative, then of course you just get a negative number, right? So you must be really wondering now, what's the connection here, because we use the same symbol for both. The only difference is that for definite integrals, we have these additional numbers. We have the upper and lower bounds, the upper and lower limits of the integrals, right? But yeah, we don't have that for the indefinite integrals, right? So other than just the notation, what's the connection here, right? And that's the fundamental theorem of calculus, right? So I'm going to scroll up and I will reveal the fundamental theorem of calculus. Here it is. All right. And this is theorem 4.9. But more importantly, I'll just refer to it as the fundamental theorem of calculus, right? So you have a continuous function on a closed and bounded interval, and your capital F is an antiderivative of little f, right? So the derivative of capital F, right, or capital F prime, is little f. So the definite integral from a to b of little f, right, is just going to be the difference of evaluating capital F at a and b, right? So let me say that again, because this here is the absolute key, right? This is essentially the fundamental theorem of calculus. The definite integral from a to b of any function, any continuous function, is the same as if you took the antiderivative as a function and evaluated it at a and b and then subtracted, right? But you're subtracting the top minus the bottom number, f of b minus f of a, capital F of b minus capital F of a, right? So that's the fundamental theorem of calculus. And I wrote the proof down here. I'm not going to go through it. It's in the book. It's not difficult. It's just taking a partition, dividing it up, and using the mean value theorem for derivatives. But it's not essential that you understand the proof, right? Much more essential that you understand what this equation tells us. And when we go through a bunch of examples, you'll see how powerful this is, right? Because it allows us to calculate these definite integrals much more simply than, the definition. If you remember, this is sort of the definition here of the definite integral, or at least it involves it when you take the limit. But after this, we're never going to have to use that again, right? We did it once. Once is enough, right? Okay, so I'm going to scroll down and write this down again, because this is the key here. And we'll do some examples, right? We'll do some examples to show you just how powerful this statement is here, right? So yeah, the fundamental theorem of calculus just says the following, that again, under the right conditions, the definite integral, I should use a different color here. We'll use this color here, right? The definite integral from a to b of any function f of x, right, is just going to be the same as the antiderivative evaluated between a and b. So this vertical line just means I still have to plug in the b and the a here. So it just means I'm going to plug in b first, then plug in a, then subtract those two numbers. Okay, so that's the fundamental theorem of calculus. Okay, so let's do some examples. First one. So let's do the definite integral from 0 to 3 of the function 9 minus x squared dx, right? So keep in mind now, my little f is the function 9 minus x squared. We call that the integrand, right? That's the thing we're integrating. The integrand, right? That's in this, right? And you could use parentheses here, although they are optional. Anything between the integral sign and the dx is the function. In this case, f of x is 9 minus x squared. Okay, right. So what do we need to calculate the integral? Using the fundamental theorem, we need the antiderivative. So what's my capital F? My capital F is the indefinite integral. And this is something that you did way back in section 4.1. So yes, right, to go through it one more time, right, this is the difference, just like the sum, you can split it up. It's the sum rule. Right? And now the integral of 9 is just 9 times x, right? And the integral of x squared is 1/3 x cubed. Just use the power rule, right? Right? Plus c. Although we're not going to need the c here, and you'll see why in a second. But so let's leave it for now as plus c. So that's my f of x, right? This is my capital F of x. That's my antiderivative of little f, right? So this is my antiderivative, right, of little f, which was 9 minus x squared. Okay, just saying that again. All right, so yeah, we have here that this is equal to capital F, which is 9x minus 1/3 x cubed plus c, although we don't need the c here. And then we have to evaluate it between 0 and 3. Okay, so what that means is I'm going to plug in 3 here into my wherever I see an x. So this is 9 times 3 minus 1/3 times 3 cubed plus c, right? So all of this is my capital F of 3. And then I have to plug in the lower number, the 0, right? So let's do that here. So we're going to take all of this, and then we're going to subtract. When I plug in 0, I get 9 times 0 minus 1/3 times 0 cubed, also plus c. And that's my f, capital F of 0. And then I just have to subtract those two numbers, right? All right, well, 9 times 3 is 27. 3 cubed is 27. 27 divided by 3 is 9, plus c. And 9 times 0 is 0. 0 cubed is 0, plus c. So now I don't need the brackets anymore. I'm just going to do 27 minus 9, minus 9 plus c, and then minus c, right? Because don't forget the minus sign distributes here, right? Well, c minus c is 0, and 27 minus 9 is 18. So that's our answer. Right? This definite integral here, when you calculate it, you get 18. All right. And this is not new. We've done this before. This same integral, if you go back to the video we did for section 4.2, and this was part 2, we actually calculated this. And if you remember, well, you may not remember, you can go back to the video. The video was over an hour long. And I'm guessing that this calculation here took probably more than a half hour, maybe 40, 45 minutes. So look how much faster this was, right? This probably took less than 5 minutes. using the fundamental theorem of calculus, which is this thing in purple, right? Using this, we were able to calculate this integral here, this one here, much faster, just by doing an antiderivative and then plugging in numbers, right? The way we did it the first time, if you remember, we had to calculate the limits as n goes to infinity of the sum I goes from 1 to n, and then we had to find the f of xi or the f of ci times delta x, and that went on for, again, at least a half hour, somewhere around there. And it was just that really long, tedious calculation that ultimately I said, yeah, don't worry about that, right? I mean, it's just to show you how terrible this is. Using the definition, just like the definition for derivatives, it's not pleasant, right? So here you go. This fundamental theorem of calculus here, right? This is our shortcut. This is a way to calculate these definite integrals without having to go through this horrible Riemann sum business. Okay, so no more. We will never have to do that again. And in reality, you probably never did it. You might have done it once for homework, but again, not really necessary that you know how to do that. On the other hand, doing a calculation like this, all of this here, is essential, right? So it's not trivial. You still have to find, right? We still had to calculate this, the antiderivative, from 4.1. We knew the rules for that. And then we just had to, use this part, plug in the a and the b, in this case, the 0 and the 3. So we did that here. And we get an answer, right? Another thing I want to point out is that, remember I said we don't need the plus c here, right? We can just assume that c is 0 in this case. And you can see why, because here we have plus c, here we have minus c. So even whatever the c is, it's the same for both, you're going to end up subtracting them, right? Because in the f of a minus f of b, you're going to get c minus c, which is 0, right? So yeah, effectively, you don't have to bother with the c's anymore when you're doing definite integral, right? When you do indefinite integrals, it's part of the answer. So I shouldn't have crossed this out here. In fact, I should have left the plus c, the plus c right here. Here, let me erase it. There we go. Yep, because I crossed it out, but I shouldn't have. What I mean by that is when you're calculating the definite integral, you definitely need the c here. But when you're doing the indefinite integral, yes, you need the plus c. When you're doing the definite integral, you can ignore the c because it's going to subtract out to 0 as it did here, right? Okay, so again, a perfect example because we did it the long way and now we just did it the short way, right? Or shorter way anyways. Okay, so yeah, let's do another one. So I'll scroll down and write down another one and see how this goes. Okay, here's a good one. We want to evaluate the definite integral from x equals 1 to x equals 8 of this function, the cube root of x plus 2x. Okay, so yep, my integrand here, this thing in here, that's my f of x. All right, so let's just write that down. Little f of x is the cube root, although we can write this as x to the 1/3, if you remember, plus 2x. And so how do we calculate this? Well, using the fundamental theorem of calculus, we need the capital F, right? We need an antiderivative. So we're going to do an antiderivative, an indefinite integral of the same function, x to the 1/3 plus 2x. And again, by the sum rule, we can split this up. But, right, x to the 1/3, by the power rule, remember you have to add 1. You get x to the 4/3 divided by 4/3. Right? And then plus x squared, right? The integral of, the derivative of x squared is 2x, so the integral of 2x is x squared, right? Plus c, because this is an antiderivative, it's an indefinite integral, so you do need the c. And of course we should clean this up a little bit. This is 3 over 4 times x to the 4 over 3, right? Plus x squared plus c. Okay. So there's my antiderivative, right? So remember, we're going to take this f of x, capital F of x, the antiderivative, and then plug in the a and the b, in this case the 1 and the 8. Okay, so this says that I already took the antiderivative. In fact, I should have written that down here. This is 3/4 times x to the 4/3, right, plus x squared. And we don't need the plus c here because we're going to plug in the 1 and the 8, okay? Right, so, yep, so we still have to plug in the 8 here, so let's do that. This is 3/4 times 8 to the 4/3 plus 8 squared, right? And then minus, right, let's highlight that, right, minus, when you plug in 1, you just get 3/4 times 1 to the 4/3, which is 1, of course, plus 1 squared, right? So, yep, this is, again, just f of b minus f of a, or in this case, f of 8 minus f of 1. So this is my f of 8. This is my f of 1. Should I highlight that? Right. All right, so what do we get? 8 to the 4/3. So that's the cube root of 8 is 2. 2 to the 4th is 16. 16 divided by 4 is 4. 4 times 3 is 12. That's right. I mean, if you don't buy that, use a calculator. But in this case, I did it all in my head, right? Plus 8 squared, of course, is 64. And then minus 3/4 times 1 plus 1. Oop, that's a 4, sorry. Plus 1. So 12 plus 64, 76. Minus 3/4 plus 1. Well, remember 1 is 4/4, so that's 7/4. Right? Although maybe I should have left it as 1 and 3/4. Yeah, maybe let's do it that way. Minus 1 and 3/4. Okay, so that's going to be what? 75 minus another 3/4, so 74 and 1/4. Or if you prefer decimal, 74.25. So I think that's it. Again, I'm not picky. Either way is fine. Right? And so remember what this number represents. It's going to be the area, right? Let's do it over here. So here's 1, here's 8. Whatever this function looks like, here's your f of x. It's going to be the area of that region, right? And you can see it's a fairly big area because x squared, or rather 2x, even though x cubed doesn't get very big, 2x gets very big. So this is not the graph of the function by any stretch. You know, it's probably concave down now that I think of it. But in any event, it's just the idea that this is an area here, right? This is an area under this curve up here, right? This function here, right? So yeah, I graphed this function very poorly, I might add, and the area under that from 1 to 8 is this number here, 74.25. Okay, yeah, I guess we should do one more. So I'll do that in a second. Okay, so next example, we want to evaluate this definite integral from 0 to pi, right? Pi is 3.14159 and so on, of sine x dx. And I even drew the picture here. This is the graph of y equals sine x from 0 to 2 pi, but we're only going from 0 to pi, right? In other words, the area, this is the area we want to calculate here, right? That's what this definite integral represents. So how do we do it? Well, we're going to use the fundamental theorem of calculus, which maybe I should write it down over here. Definite integral from a to b of some function is going to be, well, okay, so the antiderivative evaluated between a and b, that's the intermediate step here. And then you just plug in the b and the a and then subtract, right? So that's the fundamental theorem of calculus. I don't want to go through it, but we're going to use it, right? We're going to use it here. So what do we need to do? We need to find an antiderivative of little sine. So sine of x, your capital F, well, will just be the indefinite integral of sine. And hopefully you remember that that's not cosine, right? It's negative cosine, because the derivative of cosine would be minus sine. If you want to get positive sine, you want the negatives to cancel. So the derivative of negative cosine is negative negative sine, or positive sine, right? So an antiderivative of cosine is, the antiderivative of sine is cosine, right? Negative cosine, rather, plus c. Okay, so yeah, remember we're not going to need the c here, but our antiderivative is negative cosine of x. And now that we've taken the integral, right, don't do this again. I've seen people make this mistake where they do another integral. You already did one. You don't need to do it again, right? That's like taking the second derivative, right? This would be taking the second antiderivative. So yeah, don't do that again. Once you take the antiderivative, once you have your capital F, then you just use this symbol here. This line means I still have to plug in the 0 and the pi. Okay, so the top one comes first, so plug in x equals pi, right? So we want the cosine of pi, or negative cosine of pi. And then minus, well, be careful, minus a negative cosine of 0. Okay, so an awful lot of negative signs. You have to be very careful about this, right? What's worse is that, well, what's the cosine of pi? It's actually negative 1, right? And then what's the cosine of 0? That's positive 1. So yeah, you have a lot of negative signs here. Negative negative 1 is positive 1. And then minus a negative 1 is also positive 1. So you get 1 plus 1, which is 2. Right, so that's the answer. And so that's the area of this, right? The area of this region here is just 2 units. Okay. Right, two square units, 2 square meters, or whatever it is, right? Right. So yeah, very easy to do this. You just have to get used to it. And I'm going to give you a little bit of a hint here. When you have this minus in front, remember this property down here. If you're going from B to A and you want to go from A to B, just multiply by negative 1, right? So what we could have done here is instead of having this negative cosine, we could have made this a positive cosine. That would make this a little easier, but the drawback is now you have to switch these. Instead of going from 0 to pi, you're going from pi to 0. Okay, so let's do that down here since I'm running out of space. Right. So this is going to be cosine of 0 minus the cosine of pi. Cosine of 0 is 1. Cosine of pi is negative 1. So you still get the right answer. 1 plus 1 is 2. But look how many fewer negative signs there were. Right? Here we had 4 negative signs. Here we only have 2. So if you're getting mixed up with all these negative signs, maybe switch the negative to a positive, and then switch the limits. The upper and lower limits get switched. So you're going 0 on top, pi on the bottom, and then when you subtract, you get the same answer. It's still equal to 2. So I hope that helps. Okay, I think one more. We want to evaluate this definite integral. So a is negative 2, b is 6, and the function, the integrand rather, so my little f here, my little f, lowercase f, is just the absolute value of 2x minus 4. Okay, so this is going to be a problem because remember we want our antiderivative before we plug in the negative 2 and the 6. So let's find that antiderivative first. Well, yeah, see, we never had a rule for this, right? How do you find the indefinite integral of the absolute value of 2x minus 4, right? Now, I mean, the 2x minus 4 is on the inside. That's sort of a chain rule here. And remember, there's no chain rule. But the idea is we never gave you this, the indefinite integral of absolute value of x. So obviously, with the 2x minus 4, that only makes it worse. Yes. So, well, I mean, look, you can look it up. But this is something that you're not going to be able to do until Calc 2. So this is a Calc 2 problem. So without that, we're kind of stuck here, right? We're not going to be able to do this, at least using the fundamental theorem of calculus, right? On the other hand, maybe there's a way to do this, the old-fashioned way, right? Let's look at the graph. Oh, maybe I should do a better graph than that. Okay, that's a little bit better. I need to make this a little longer. Okay, good. So this is my x-axis. This is my y-axis, although I just realized this is going to go way up even further here. So my scale is going to be a little bit off here, but let's make this -2, and then -1, 1, 2, 3, 4, 5, 6, and we can end at 6, right? And now we need to graph this function, right? This absolute value of 2x minus 4. And so remember what this is, right? This is the dividing point here is 2, which I think is right in the middle here, is 2. Yep, when you plug in 2, you get 0, right? So f of 2 is 0, so that's the x-intercept, right? And then you just have the graph of the line, 2x minus 4, at least when x is bigger than 2. So 2x minus 4, well, if you plug in 6 here, what do you get? You get 12 minus 4. 12 minus 4 is 8. So we have to go all the way up to 1, 2, 3, 4, 5, 6, 7, 8. Oh, we could have gone higher, but okay. 2 times 6 is 12. 12 minus 4 is 8. Okay, that's right. So yep, this will be the point up here, 6, 8. And we know it's just a straight line. Now you can see that, oh, I missed. All right, close enough. You can see that this line here should have a slope of 2, and it doesn't look anywhere near that steep, and that's because I changed the scale a little bit. So, right, I squashed the vertical scale. So ordinarily, this line should be a little bit steeper, but, you know, because I changed the scale, it's fine. So what happens when x is less than 2? Well, this is going to be, right, so this is 2x minus 4. Now we're going to get 4 minus 2x. Right. And of course, if you plug in -2, you get 4 plus 4 is 8, so you get the same thing, right? And of course, if you plug in 0, I think you go right through 4, so you get this line here. Pretend it's a straight line. Yep, so this is -4, 8 as well, right? So you get this V-shaped object, and we just want to go from -2 to 8, right? And so we want the total area of this region here plus this region in here. And that will be the value of the definite integral. Well, notice that this region here is just a triangle, right? This is supposed to be a triangle. The base is 6 minus 2, which is 4. And the height, well, it ends up at y equals 8, right? From 0 to 8 is 8. So 1/2 the base times the height is 1/2. The base is 4, the height is 8. So that's just going to be 2 times 8 is 16. So the area of this region here is 16. Plus, what about this triangle here? Well, it's by symmetry, it's the same thing. But if you don't believe me, you're going from -2 to +2. That's also 4. And the height is also 8. So you're just doing this again, 1/2 the base times the height, that's base is 4, sorry, times the height is 8, that's also 16. And so 16 plus 16 is 32, and that's the answer to the definite integral, right? So here, right, we did not use the fundamental theorem of calculus. We didn't do it this way because we ran into this little problem here that we didn't know the antiderivative of absolute value of x, and so we couldn't find the antiderivative or an antiderivative for absolute value of 2x minus 4. We simply don't have the formula for that just yet. Again, that's something you might get in Calc 2. But without that formula, right, then we were just not able to do the fundamental theorem of calculus. We had to do this by finding the areas of these two triangles. And the triangles happen to have the same area. So you just double 16. Okay, so yes. So when you see something that you don't know how to do an indefinite integral for, you simply have to find some other way. And in this way, we could do it by just finding the areas. But for more complicated functions, you might not even be able to do that, because what if your function is a curve like this? Then you're not going to have rectangles or triangles anymore, so it's going to be more complicated. And in general, there are techniques for approximating integrals when finding an antiderivative might not be feasible. Okay, so that's the drawback to the fundamental theorem of calculus, right? Just to highlight this over here, right? In order to use the fundamental theorem of calculus, you have to be able to find an antiderivative, right? This capital F of x, right? We were able to do that here in the previous example, right? The integral of, or the indefinite integral of sine x is just negative cosine x, right? That you should know by now, right? But we didn't know how to find an antiderivative of absolute value of x. And because of that, we were stuck. We couldn't do this fundamental theorem here. We had to do it the old-fashioned way that we did in 4.2 and 4.3. So yes, so obviously this fundamental theorem of calculus up here, it's not a, you can think of it as a formula, but it's a formula as long as you know how to find this capital F of x. If you can't find that capital F, it's useless. So obviously this won't work for everything, right? It only works when you know your antiderivatives. If you can't find an antiderivative, right, then you can't use the fundamental theorem of calculus, right? You might actually have to go back and calculate that Riemann sum business. Well, I'm sort of half kidding there. You're not going to have to do that, but you do have the definition to fall back on, right? Remember, the definition is this. I'll do it this way, right? Is the limit as the norm of the partitions go to 0 of the Riemann sum, I going from 1 to n, right? So, of course, this definition will always work, but again, this may not be practical either. Okay, so this might not be the best way to do it either. Okay, so yes, for calculating definite integrals, right, the easiest way would be if you have your antiderivative, to use the fundamental theorem of calculus. If you don't have that, well, maybe it's just a simple area like a rectangle or a triangle, or maybe part of a circle, right? Maybe part of a circle. You can do that too. There's probably that in the homework. So, but that's basically it, right? So maybe I'll do one more definite integrals using the fundamental theorem, because that's probably the easiest way. Okay. All right, so we want to evaluate the definite integral from -1 to 3 for x squared minus 6x squared minus 8x, right? Right. So let's do this a little bit faster here, right? We know the integrand is 6x squared minus 8x. What's your antiderivative? Well, using the power rule, right? This is 6 over 3 times x to the 3. And then same thing here. This is 8 over 2 times x squared. So when you simplify that, you just get 2x cubed minus 4x squared. Okay, so that's my capital F of x. Oh, plus c, but we're not going to need it here. So this is going to be 2x cubed. I'm going to make that a little bit closer here, right? 2x cubed minus 4x squared, right? And then we don't need the c, but what we do need to do is plug in the 3 and the -1. Okay, so let's do that, right? This is going to be 2 times 3 cubed minus 4 times 3 squared. Okay, so that's my capital F of 3. And then we have to subtract capital F of -1. So let's do that here. I'm going to use brackets so we make sure we have the minus sign in between. Okay, so 2 times -1 cubed minus 4 times -1 squared. And when you just evaluate all that, let's see what we get. 27 times 2, I think, is 54, unless I'm mistaken. And then 9 times 4 is 36. right? And so this is negative 1 cubed is negative 1. Negative 1 times 2 is negative 2. And then negative 1 squared is positive 1. So negative 4 times 1 is negative 4. Okay. And then we get 54 minus 36, which is 18. And then negative 2 minus 4 is negative 6. So, yep, you just get 18 minus negative 6, which is 18 plus 6, which of course is 24. Okay, right. Now keep in mind, right, we've seen problems where you get decimals as well, but, you know, in a lot of cases you'll get a nice whole number, but you can get fractions, you can get decimals for your answer. That's not uncommon. Right, but in this case we get a nice number, 24. Okay, so I hope we're used to that for definite integrals. Just use the fundamental theorem of calculus. And I used it here without writing it down. But way up, well, I messed it up already. But here it is again, right? And so, right, so the basic idea is just to do the definite integral from a to b. Right? So don't forget, find your antiderivative, your capital F, and then plug in the a and the b, and then just subtract. Right? Remember, top minus bottom here. Okay. Yeah. Now don't forget to find the indefinite integral. In other words, you don't plug in the negative 1 and 3 into this, right? So don't make this mistake, right? Because this is the original function. This is the integrand. It's not your antiderivative. It's not capital F, right? This is your lowercase f, little f. This here is your capital F. So yeah, you can't plug these numbers into the original function. You plug them into the capital F, the antiderivative here, right? Okay. So I think that's it for what was this? This was section 4.4. Actually, I'm going to make one more video because we have a lot more properties. And so this will be part 1, and let's go on to part 2, which will be more properties of definite integrals, integrals in general, and just things that might come in handy. So rather than try to make one long video, I'll make a couple of short ones.